Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello, thank you for choosing IT Pro TV, empowering the world with engaging learning. I'm Zach Mimis, your host, as we continue on with CompTIA Net Plus. This is IPv6 Addressing, and the person bringing us the information we need, the one and only Wes Bryan.
Hey, Zach, how you doing? Thanks for having me back. That's right. You know, we have been talking over the last few episodes a lot about the Internet Protocol addressing, right? But we've been really focused on IPv4, right? The long-time Internet Protocol addressing solution, right? So we're going to kind of diverge off the beaten path that is known as IPv4, and we're going to make our way into some of the concepts surrounding the IPv6 addresses and the IPv6 address types in this episode.
And so that leads to this question: why do we need IPv6?
Well, you know, that's a great question. You know, when it comes down to it, you know, you look at IPv4. IPv4 has some limitations, right? The very first thing that it has when it comes to limitations really boils down to, well, how many bits do you have available, right? When we looked through all the different DNA or the structure of an IPv4 address, right, we said that it is a 32-bit address space, right? And we know that by now, right, our computers speak binary, so everything's an exponential value of that base 2 numbering system, right? Well, 2 to the power of 32 gives you around 4.3 billion possible addresses, and it's a little bit under that. It's 4.294 billion and change, right? It's the same limitation when we talk about, why do 32-bit operating systems, why can they only see 4 gigs of RAM? Well, when you look at the 4 gigs of RAM, that limitation is based on how many of those memory addresses that we can get within a 32-bit space, and within that 32-bit space, it's 4.3 billion memory addresses, which puts us right at 4 gig RAM limitation, right? Well, IPv4 has that same type of limitation, and the fact that you only have so many possibilities within a 32-bit addressing space, right? The other thing, too, if you're not aware, if you're not aware of the classes, right? We talk pretty heavily about the classes, the classful addressing space. We talk about A, B, C, D, and E, right? Well, if we look at the last two, Class D and Class E, well, Class D, we don't really allocate those addresses to any one computer or a series of computers in general, right? That's the multicast addressing space, and all computers use that on an IPv4 network, right, to communicate multicast communications. Well, because of that, that means there's one block that's completely reserved for multicast communications, and then the last block, E's, really isn't given out to any computers, right? That's for scientific purposes, research, experiments, if you will. So we have 2 of those 5 blocks within the IPv4 address space that we don't even allocate to computers. So it really just means that we have A, B, and C. All right, well, at the time that the internet came, you know, I say internet, back days of ARPANET, right, before the internet boom, right, the .com boom, 4.3 billion addresses was really enough, right? We only had 5, 6, maybe 10, you know, just a handful of organizations that were really even connected to the internet in those days, or the networks in those days. So there really wasn't much concern that we were going to, you know, eliminate, or we were going to exhaust all of those IP addresses. But as the exponential growth of the internet evolved, right, we got through the .com bubble, that .com boom, it was pretty understood that we were going to exhaust all of those, that 32-bit address space, right? That's why they put in things like RFC 1918, which allowed us to use those private unregistered addresses you could use at your leisure within each of the classes internally on your local area networks. But you couldn't communicate across the internet, and RFC 1918 also introduced network address translation, right? We talk about NAT, a way essentially that you can take a single public IP address, and behind that you can have multiple private IP addresses sending information through the device that would provide network address translation. So the engineers there of the internet, they said, hey, we're going to have to come out with something that is going to essentially replace this earlier system, which we're not going to have too much longer. And they came out with IPv6. I'm not sure what happened with IPv5. I don't know if it wasn't good enough, it wasn't cutting the mustard, but we have IPv6. Now, We got to know a little, some of the facts about IPv6, all right? And one of the things that I want you to know is if we compare the address spaces, right? We look at the address space, a 32-bit address space, you will see that if you were to take each one of those possibilities, convert them into their own grain of sand, all right? And then you were to take all of those possibilities, you could pretty much get a container that's the size of a small moving truck and barely even fill it up and have a lot of room left over, right? If you look at the IPv6 address space and do the same thing, take each one of the possibilities that you have within this space, this gigantic space that we'll talk about, and you could convert them, each one of those, into their own possibilities. You'd need a container that is 1.3 billion times the circumference of our Earth to be able to contain all the possibilities.
Bigger than the Earth, then.
That's right. So when they came up with the successor, if you will, to IPv6, well, they came up with an address space that is fairly big, right? Let's take a look at some of the makeups of IPv6 here, all right? First of all, it's a 128-bit address space, all right? 128 bits. Right, there are so many possibilities there that if you were to convert each one of those possibilities, there's another one that analogies, honestly, Zach, don't even make sense.
No,
Our minds cannot comprehend how big this pool of addresses is. It's actually 340 undecillion, I believe it is. It's like undecillion, right? Wow. It's an actual number, believe it or not. I think it's like 12 place values above a billion, right? So it's astronomically large, all right? And if you were to take those possibilities and convert them into those little BBs, right, that you'd shoot in like the old daisy repeaters, and you would form a line just side by side. That line would go to the center of our galaxy, wrap around the nearest black hole, come back, and we'd still have millions, if not billions upon billions of possibilities or BBs left over. So they definitely overshot the runway here. They wanted something that says, hey, we've got the next generation addressing protocol, and there's a good chance we won't use any of the, or exhaust the entire pool. So 128 bits. Now, I want you to know that it's a little bit different than our IPv4 address. It's written in hexadecimal value. All right, and hexadecimal value, keep in mind that's a the base 16 numbering system, right? And we talk about base 16, that means we have, what, 9 possibilities, then we have A through F as well, right? So again, just keep in mind that it's a little bit different than what we see in dotted decimal notation. This is actually termed as colon hexadecimal notation, right? One of the great things about this, too, is that the computers, depending on what type of IPv6 address you're talking about, can have multiple IPv6 addresses at the same time, right? When we talked about IPv4, Zach, on many different occasions throughout this series, one of the things that we said is you have a single IPv4 address, right? Now, you can have different types of IPv4 addresses, right? You could have just a single IPv4 address, or if you couldn't communicate with a DHCP server, you might have a PIPA address, but the format follows the same. I only have one that's going to be preferred over the other, all right? Not so with IPv6. In fact, let me go ahead and kind of show you what I mean. I'm going to switch over here to our Windows 10 machine, get logged back in, and we're going to run a utility that we've been running for a while when it comes to looking at the parameters, right, the Internet Protocol parameters of your network adapter. So, for instance, if I run ipconfig, I'm not going to run the all option here, just basic, just run it easy and breezy here. But one of the things you'll notice is that, well, look on this one adapter here. We'll talk about what this actually means coming up here in a second. But notice that I have 2 different hexadecimal or colon hexadecimal IPv6 addresses right here. All right, which is kind of great. It's kind of interesting that the way they've made this IPv6 work, you know, and you can actually see that I have quite a few, actually. I've got one here, a link local IPv6 address, and you can see I also have another IPv6 address. So just keep in mind that you can have multiple IPv6 addresses at the same time, and depending on where you send the traffic, will dictate which one of these that you use.
And in fact, and maybe you've already mentioned this in I just missed the brain. It kind of jumped the shark, if you will. Are there the same address types in IPv4 as there are in IPv6?
Well, when you think of communication types,
yeah,
absolutely there are. When we think about, like, for instance, communications, you have a few different types of communications. In fact, let me switch back over to my diagram. I tell you what, let's go ahead and let me talk a little bit more about the structure of the IPv6 address, and I want you to hold that thought because we're going to come back to it once we know the DNA, if you will, the makeup of an IPv6 address. All right, now, one of the things is to understand what the IPv6 address looks like is understand that it is 8 blocks, all right? When we say 8 blocks, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 blocks, all right? The blocks are expressed in hexadecimal value, and what each block actually represents is 16 bits underneath, right? So 16 times 8 makes 128. So this is an astronomically large address. In fact, I'll put IPv4 addresses in an Excel spreadsheet. I'm not going to bore you with that. I mean, it'd be so long, we'd have to zoom out. I don't even know if we could actually see it when zooming out to see this address on how big it would be, all right? Now, one of the great things about this is they've actually put methods in place that will allow you the ability to actually abbreviate this address to make it a little bit easier to work with, right? And one of the things that I want you to first of all pay attention to are what are known as leading zeros. Notice that we have a 0 out in front of this 8 here, a couple of zeros out in front of the 54 here. And really when it comes down to it, we've got 3 zeros in front of this block, 3 zeros in front of this block, and they're all leading zeros, right?
Right.
So one of the first things that you can do when it comes to abbreviating an IPv6 address, notice that here is our non-abbreviated address. The first thing you can do is you can remove all the leading zeros, and see if I can get both of those in the screen here so we can see what exactly is going on here. Now notice what I did. Notice there are 3 zeros here in this address. Notice that I just removed them. I replaced that with a single 0,
Yes.
right? We have 3 additional contiguous 0 bits here. I removed those 3 leading zeros in that block as well. Likewise, with this third block of zeros, I basically abbreviated the first 3 leading zeros there. Notice, remember what we said, I got a 0054 here, right? Well, I can actually remove those leading zeros in the address too, and we can replace that with just a 54. Notice that we also have our 8, right, 08DE. Well, I can remove that likewise too. So you can see that the address becomes a little bit more manageable, right, as we start to remove things like the leading zeros. Well, one of the great things that we can go a little bit farther, and it can make it a little bit easier to work with, additionally, to work with this IPv6 address is basically truncating blocks of zeros, 0 blocks, if you will. Notice that in the original non-abbreviated address, we actually had these 3 blocks of contiguous zeros. All right, and one of the first things you can do is remove those leading zeros, right? So it's just 3 zeros now. But we can go even farther there. We can take those 3 zeros because we know they are contiguous blocks of 0 bits, and we can actually truncate them even more and replace them with a double colon. Now, notice that we've gone even farther, removing the size of this address, abbreviating it, if you will. Notice that we now went from 8 blocks down to 1, 2, 3, 4, 5. Now, I will tell you that that double colon right there, it can only appear, right, in one, or in the address one time, excuse me. And the reason is because your computer will look at that double colon and it'll say, all right, well, how many blocks do I see within this address right now, right? And the abbreviated form. Well, we just kind of counted that, right? We got 1 block, 2, 3, 4, 5. So the computer says, oh, I see that double colon, all right? And what that means is that to rebuild this address when your computer's working with it, it'll look at the double colon, and then what it'll do is it'll say, oh, I know those are 3 contiguous blocks of zeros, and it'll rebuild the address, right? So just like we talked about in our IPv4, right, we talk about dotted decimal notation really being a way that you and I, Zach and I, we can read these addresses rather than having to remember the 32 bits of binary. Well, even in colon hexadecimal, it's still a pretty darn big address, right? So they've given you ways that you can start to reduce the size of that address even more, all right? So that is important to remember that you can do that. And we're going to talk about some other kind of addresses that might not really look like valid addresses, but you'd be surprised if you know what the abbreviated form is. So let's go ahead, and the next thing I want to talk about is, well, what makes up an IPv6 address? Well, you have 2 components, just like we do when we talk about IPv4, right? All right. Remember in IPv4, we have a certain amount of bits, and this is denoted by our subnet mask, right? We have a certain amount of bits that are going to be our network portion, right? We have a certain amount of bits that are going to be our node portion. All right. Now we can also use CIDR notation, and we can just use the slash, let's say 24, and that tells us how many 1 bits are in the subnet mask. Well, you have to know that with an IPv6 address, what we use is CIDR notation. CIDR notation essentially is just the slash at the end of it. It tells you how many bits are reserved for the network portion, and by default, you have 64 bits that are part of the networking. You have 64 bits that are part of what's known as the interface ID. Think about it, the interface ID as being like the node portion of an IPv4 address, right? So, and then within that network ID, you could break that down even farther. That's one of the great things about IPv6 is that it's got that hierarchical routing blocks, if you will, and it makes it much more efficient when it comes to routing information over IPv4, right? So you might see that in some documentation that they'll take and they'll say, okay, so the let me get the right arrow here. You might see, I'll get that out of there eventually. You might see something like this where they say, hey, this portion of the address, if I can move that over just a little bit more, you might see something like this where they say, hey, this portion of the address is what's known as the routing prefix, right? Because you can go even farther than that. And then in here, what you might end up having is something like, and let me move these over here just a little bit more, you might have something like a subnet ID. All right, so I don't know that if they'll get that specific on the exam, but keep in mind that still doesn't change the fact that that whole portion, that whole 64-bit portion is a part of your network identifier. All right, so do keep that in mind on how, you know, the components or the pieces, I should say, inside of your IPv6 address, because that is important. Mm-hmm. Now, I want to go back to, Zach, you asked a great question. You said, you know, just like in IPv4, right? You said, you know, do we have the same type of communication?
Yeah, address types.
Right? Yeah. And we do, right? And what this is essentially is what types of communications do we have, right? Well, one of the great things about IPv6 is we still have our one-to-one communications. That doesn't change. That concept is the same, right? And that's a unicast address. All right, you also have multicast addresses too. All right, and when we say multicast, it's the same thing, right? Multicast communication is a one to a specific few or a group, one to many, if you will, that multicast communication. And then we also have what's known as anycast. And anycast, I kind of talked about just briefly in the IPv4 as being a certain type of transmission. Understand that anycast is a one to the best, one essentially to the best, right? Or to the nearest, based on a routing table, if you will. Now, I will tell you one thing that is different than IPv4. IPv6 is more efficient because it eliminates broadcast communications. The things that we used to do with broadcast communications that would potentially waste our bandwidth if we get broadcast storms that can cause all kinds of problem loops, if you will, are actually eliminated in IPv6. So for instance, you'll see things like ARP. You say, well, wait a second, how does address resolution protocol happen, right? Well, ARP is interesting because it's kind of built into ICMP, and ICMP is working over multicast communications inside of IPv6. So no broadcast communications. I want you to remember that on the exam. That is something that very well could come up, and they could ask you, hey, you know, broadcast communications, are they allowed? Just know that they are basically eliminated inside of IPv6, and that is important. All right, so those are our, you know, when they talk, our address types, again, unicast, multicast, anycast, broadcast is eliminated. Now, we also have to be aware of IPv6 address scopes, all right? And when we say a scope, I want you to think of inside of IPv4, right? Inside of IPv4, we've got a set of addresses, right? Certain amounts of these addresses or certain types of addresses are allowed for internet communications, right? Certain addresses that we have are only allowed for your local area network communications. Sometimes you'll see some of the addresses we have are when we don't have a DHCP server present, right? And it is important to understand that depending on what type of communication you use will dictate which of the address scopes you might be using, all right? There's 3 scopes that I want you to be aware of for this exam, all right? There is what's known as the global. All right, global unicast addresses. When we talk about global addresses, what we're talking about is these, if you want a comparison back to IPv4 and what you've already learned with IPv4, I want you to think of your global addresses as being like your public addresses. You might hear them called global unicast internet addresses, right? And that means we can send and route information across the internet just like we can with the public IP addresses that we talk about in IPv4. All right. Now we also have what are known as unique local addresses. All right, when we talk about a unique local address, you want to understand that these are used for internal communications, right? When we talk about internal communications, your unique local IPv6 addresses, if you need a way to kind of consider what they are or compare them back to IPv4, I want you to think of them as the private IP address space. Right, remember we said with a private IP address space, I can use them at my leisure within my internal network to communicate, but what I can't use those private addresses to do is to route traffic across the internet, right? That's where we add technologies like network address translation. Well, that's what your unique local addresses are. Your ULAs, as they call them, are your basically like your private IP addresses that would be used within your organization only. Then we have what's known as the link local address. All right. When we talk about the link local address, remember one of the ways that we said that you could you could still obtain an IP address if you couldn't communicate with a DHCP server. We said you could have an APIPA address. All right. And the APIPA address is how you could communicate with another computer on the same subnet as you if there wasn't a presence of a DHCP server, but you could only communicate with other computers on that APIPA network, right? Well, the link local is interesting because this is used essentially to communicate with nodes that are on the same subnet as you. All right, if I need to talk and let's say my computer and Zach's computer are on the same subnet and we need to communicate, right? Well, there's no reason to use a global unicast address, right? Why? Because we're not communicating across the internet. All right. We don't necessarily need a unique local address that could be routed across multiple internal subnets within your organization. If we're already on the same subnet, then what we can do is use additional technologies to discover what unique link layer addresses are out there and if a neighbor is reachable. And once I have that address, that link local address, I can communicate directly with Zach's computer. And I don't need to use any one of the other addresses. And the great thing is, too, like I was saying, is that with your IPv6 scopes and your IPv6 addresses, you could be using more than one address at a time. All right. Now, one of the things that we do want to also notice or also know, if you will, is a little bit about what are known as IPv6 routing prefixes. And there are a few of them here. Remember that the slash notation at the end is just like our CIDR notation. It tells you how many bits are reserved for the network, right? And depending on the type of address that you're talking about will dictate, you know, which one of these prefixes that you might have. All right, so I want you to be careful with the very first one, right? In the very first one, this is what is known as the default route. All right, when we talk about the default route, you probably remember when we said IPv4, right? When we said IPv4, the default route was 0.0.0, right? That's IPv4. What I want you to know is that, well, guess what? IPv6 also has a default route. And let me go ahead and jump back over to our routing table here because I want you guys to be able to see this. And again, compare it back to our IPv4 episodes that we were talking about. If you're not aware of those and it doesn't make sense what I'm talking about IPv4, definitely check those out. But you'll see that there's a lot of times I'll run, quite a few times I've run what's known as the route print command. And the route print command shows us our routing table, right? And in IPv4, one of the things I told you is you have this default route, right? This default route says that if my computer can't find the destination address in the packet on the local network, within the loopback network, or in this case within the multicast addresses, right? It doesn't know routing. That's not its job. So what it does is it says, okay, where do I need to send this to get this off of my local network because I've looked at the destination here and it's not my local network. Well, remember it uses the default route, which essentially is when you have a default gateway assigned to your to your network adapter, which is the IP address of the router, you send traffic to that default route. It says, I don't know what the destination network is. Let me just send it to this route. Well, believe it or not, inside of IPv6, and let me make this a little easier here. We'll do a little route print, and we will just kind of format that a little bit easier. We'll just take route. We'll take IPv4 completely out. I want you to notice that the network destination here, right? It says : :/0. Boy, that is a weird format, right? Well, what does : mean? Well, I want you to remember that what that means is that I have 8 contiguous blocks of zeros. It still follows the truncation method or the abbreviation method, because if I have 8 blocks of zeros, : says there's all contiguous zeros. So I want to kind of get you prepared on the exam for this, and then it looks like we might have to go into a part 2 here, Zach. But I want you to remember that the default route here in IPv6 is a little bit different, right? When we talk about the default route in IPv6, while the structure or the numerical value looks a little bit different, the concept is still the same here. I'll get this working right here eventually. But what you'll see here is there's a couple of different ways that you could write this out. One of the ways that you could write this out is quite literally 1, 2, 3, 4. Let's see here, 1, 2, 3, 4. And bear with me here on this one. 1, 2, 3, 4. 1, 2, 3, 4. I don't know that if I even got that close, but we'll look, and we'll do a little bit of adjustment here. All right, so there, I think I got close to doing 8 contiguous blocks. 1, 2, 3, 4, 5, 6, 7. Oh, I was just off by 1. I guess with the extra zeros, you might consider it 8 blocks. All right, so again, thank goodness for the the abbreviation mechanisms or methods, if you will, that we got here, because an IPv6 default route would look like this. Notice the concept is the same. It's still all contiguous zeros. But I want you to realize that, right? They might write this out on the exam just trying to find out, do you know that, hey, that is the default route? And do you also know that these are the same addresses, right? I can do my full abbreviation, right? I could do the opposite side where it's no abbreviation at all. But then you could go as far as saying you could do a smaller abbreviation where you do like this. And let me make sure I got 8 in there. It looks like I'm missing just 1. 1, 2, 3, 4. Oh, no, I guess I did have it right. Okay, there we go. That all 3 of these addresses are the same. 1, 2, 3, 4, 5, 6, 7, 8. Make sure I had that right. But I take the time to tell you this because if you haven't seen this format before, you might get into the exam booth and they say, which of these is the default route? Well, ladies and gentlemen, just know for your exam that these are the same. These are the same addresses, all right? This is abbreviated as far down as it can be because it's contiguous 0 bits. This is an unabbreviated default route, and this is, I guess, these are my own terms here, by the way, semi-abbreviated IPv6 default route. So that's one of the prefixes that you definitely have to know about. We've got more to talk about, but Zach's telling me over here it might be time to go into a part 2.
Wonderful job as usual, Wes. Thank you very much. IPv6 addressing. This has been part 1. There will be a part 2. Make sure you watch both of them. In fact, make sure you watch everything inside the CompTIA Net Plus series that Wes has put together for you. It will help you in the exams here and when you're doing the exam. And by the way, when you're in the course library, there's hundreds of videos there. They're all designed to help you. So take advantage of that too. And tell everybody you know about IT Pro TV. IT Pro TV is binge-worthy. Thanks for watching. I'm Zach Memis.
And I'm Wes Bryan.
And we will see you soon.
Thank you for watching IT Pro TV.